Greetings, Internet Scholars. This is your Jesse Styles, and welcome to a very special episode of Twisted Signals. Today, we are going to be talking about filters. What are they? What do they do? What is a filter? So, you know what a coffee filter is, maybe? A filter is a thing where some stuff can go through, but other stuff cannot. So when you have a coffee filter, the liquid can go through the coffee filter, but the coffee grinds cannot. So they stay on the other side of the filter. So in signal processing, filters are like this, but instead of talking about liquids, we're talking about frequencies. So the way that we have visualized signals thus far in these lectures, usually we're graphing a signal in the time domain. And when we're doing that, our graph, the y-axis, is going to be the amplitude, which is kind of like a measurement of the energy of the signal. But the x-axis is time. Filters, when we draw what a filter does to a signal, usually we're making a graph in the frequency domain. So in this case, our x-axis is frequencies. So on the left side of the screen, we see low frequencies, and on the right side of the screen, am I pointing the right way? We see high frequencies. So when we draw a filter like this, what we're doing is we're showing the response that the filter is going to have to different frequencies across the spectrum. So let's look at some basic types of filters, and we're going to apply these to an audio sound. So in the world of electronic music production, the low-pass filter is going to be a pretty familiar sound to you. So the parameter I'm adjusting here is the cutoff frequency of this filter. It's also sometimes referred to as the center frequency of the filter. And you can see the graph is showing us the response that this filter will produce across the spectrum. So down here, the response is going to be flat. So the signal will be increased or decreased by 0 decibels. And then everywhere else, you can see it's either going to be boosted by a certain number of decibels or attenuated by some amount of decibels. So this is the center of that response, where the cutoff is going to start. So a low-pass filter is so called because low frequencies pass and high frequencies are removed. So what we're doing to this sound is we are sucking out all the high frequency components. And if you look down here, this is our time domain representation of the signal. We've got before and after. So our original signal has all of these like jagged components to the waveform, these kind of like hairy little sections of the sound. And those are the parts of the signal where the amplitude is changing really, really quickly. Those are high frequency components of the signal. High frequency meaning like we have a fast rate of variation at those moments in the signal. When we run it through a low pass filter, you can see the result is this kind of like smoothed out version of the signal. It still has the same overall shape, but all of those jagged components of the signal, which are the high frequency components, have been filtered out. That's a super iconic method in electronic music production, to use a low-pass filter to change the timbre of a sound over time. Let's listen to a couple other iconic filters that we can use on sounds. A high-pass filter is like the opposite of a low-pass filter. So in a high-pass filter, high frequencies pass and low frequencies are removed. And if we look at the before and after version of the signal down here, you can see the low frequency components of this signal have been removed. And those are going to be the parts of the signal that are where you can sort of see it getting offset from the x-axis. And so the result is kind of sitting flat on the x-axis, and the only aspects of it we see are the rapidly varying parts of the signal, which are the high frequency components. So you'll hear DJs do this a lot when they're like switching from one track to another. They'll use a high pass filter, which is kind of like, that's a good trick if you want to go from a song that's in one key to a song in a different key, because the high pass filter kind of like takes the bass line out. And for a lot of people, the bass line is the reference for like what key we're in. So if you can kind of like put the song in this high pass filter world for a couple of measures, you kind of lose track of the tonal center, and then you can drop in a new song in a different key, and you know, you can get away with it that way, even though musically that transition would otherwise not make sense. Some other filters, a band pass filter. A band pass filter is sort of like a low pass and a high pass filter glued together. So you just get this band of frequencies that passes through it. A band stop filter looks like this. Peak notch filters. All of the filters. So let's look at sort of like mathematically, how does this work? So what could you do to a signal to remove the high frequency components of it? So to look at this, we're going to just generate some random numbers. We've got a metro banging this random, and I'm scaling them into this range of 0 to 1. And let's make it run quickly. Okay, so there's a bunch of just totally random values. This signal, in fact, is noise. Noise is like when we have a random values in our signal. So the noise has a lot of high frequency components, because the value of this signal could go from any value to any other value. And those parts of the signal where it like rapidly changes value are high frequency components of the signal. So if we wanted to kind of smooth out this signal, that would be a low pass filter, where we're removing those rapidly changing parts of the signal. And the way that we do that is by averaging the current value of the signal with previous values. So if we took this value, let's slow down this output again, and then we took the previous value, so bucket is an object that allows us to output previous numbers from a data stream. We've got the current value here and the previous value here, and we just did an average of these two. So here's an expression that sums these two floating point numbers together and then multiplies by 0.5. That's going to start to smooth out the signal, because if the value changed rapidly, if it went from 0 all the way to 1, the output, instead of going like a full jump of 1, it's going to be a maximum jump of 0.5. So the ability of the signal to change rapidly is being reduced just by averaging together the current value with the previous value. So this is the difference equation. Y of n is equal to 0.5, so this is like a kind of coefficient, multiplied by this, the current sample in the previous sample. If we wanted to do even more smoothing of the data, the way we do this is by using more previous values. So here's our filter where we average the current value with the previous value. Here's a version where we average the 4 previous values. So we've got a bucket with 4 outputs, and we've got an expression that sums 4 numbers and then divides by 4. So let's see if that's smoother. So just like looking at these sliders, this is starting to look smoother. And if we ran this into our version with 8 previous values that are all averaged together, this is actually like starting to turn into a fluid line. You can actually see the low frequency components of this signal because this is a low pass filter. We're just taking previous values of the sample, summing them and scaling them in different ways. And then finally, this is the convenient way to do this in Max, as this object called slide. So slide basically does the same math here. It does exponential scaling. You can read about it in the reference page. And it takes 2 arguments. So one is going to be a upwards smoothing factor, and the other is the downward smoothing factor. So we could like say a very high upward smoothing factor and then a very low downward smoothing factor. So you can see the signal can move down very quickly, but it moves up slowly. And vice versa. If we said like 1 and 100, it'll move up quickly, but move down slowly. And if they were both at some kind of moderate value, again, you have a low pass filter. We started off with noise up here, and we have filtered it out using slide, which is just taking a running average of our signal. So if we wanted to make our own low pass filter, but use this on an audio signal using MSP stuff, this would be the same basic thing here. We're going to take our sound, we're going to delay it by 1 sample and add it together with the current sound, and then we'll delay it again by 1 sample and add that together and delay it and add it and delay it and add it, and then finally divide by 4. So here is our difference equation. It's 0.25, and then it's the sum of the current sample with the previous and the previous and the previous. So let's listen to it, starting with the unfiltered sound.
Back to the thing, son define 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 back to the thing, son define.
So that's a little bit subtle, but you can hear the difference. The filtered version has some of the high frequencies removed. Okay. Let's quickly define an important type of signal called a impulse signal. Click tilde is an audio object that can create an impulse signal. So let's listen to click tilde and turn on audio processing. So hopefully you can hear that. You can see it in my time domain graph. An impulse signal is a signal that goes to a maximum value, so the amplitude is 1, instantaneously, and then it goes right back down to 0. So it's high for 1 sample, and then it goes down to 0. And when we play that through speakers or headphones, what it sounds like is a click sound, because what it's doing to the speakers is it's like making the woofer get pushed out instantaneously. So an impulse signal is a sound that goes bang, where it's like loud, very, very briefly. If we wanted to look at an impulse signal, it would look like this. So it would be an image where the brightness is instantaneously bright and then immediately goes down to 0. So we can describe filters in terms of how they respond to an impulse signal. There are 2 basic types of filters, the FIR and IIR, which stands for finite impulse response and infinite impulse response. And so the difference is whether or not these 2 filters use feedback. In an FIR filter, a finite impulse response, there is no feedback. So in fact, this demonstration patch is an example of an FIR filter. There's no feedback here. It's just feeding forward, and there's some scalars for the feed forward signal. So we take our input and we delay it and delay it and delay it. We have some coefficients to scale them, add them together, and you get your output. That's a FIR, finite impulse response filter. A infinite impulse response filter will do the same thing. So you'll take your input signal and delay it and scale it and so forth. But it will also implement feedback. So we'll take the output of our system and feed back the output, and we'll scale that by a feedback coefficient, and then we'll delay it again and scale that by a feedback coefficient, and so forth. We'll do this as many times as we like, and the output will be the sum of the feed forward signal with these scalars and the feedback parts of the signal with these scalars. So we've already built patches that conceptually do this same thing, where we take an audio signal and we delay it and use feedback. But when we do this, these delay times, these units are milliseconds. When we're making filters, the time scale is on the level of samples. So in audio, a sample is going to be 1/44,000th of a second. So much faster than the delay line is working here. So this is the filter we started off with. It's called Biquad tilde. And Biquad tilde takes these floating point numbers as arguments. And now we can actually make sense of what these floating point numbers are. They are the coefficients for this equation. So Biquad is a filter that is very widely used in the field of signal processing, and it generates a signal thusly. The output, the y of n, is going to be our input, x of n, scaled by this coefficient, plus x of n minus 1, scaled by this coefficient, and x of n minus 2, scaled by this. And then we actually subtract this feedback, so this is y of n minus 1, scaled by this, and we subtract this, y of n minus 2, scaled by this. So in Biquad, we see those 5 coefficients written here. A of 0, A of 1, A of 2, B of 1, B of 2. And by precisely setting these floating point numbers and plugging them into this equation, we can build any of the filters we demoed at the beginning of this lecture. So let's just apply this. This is an example of an infinite impulse response filter because it's using feedback. And let's apply it to this impulse signal. Okay, so here is a low pass filter with this cutoff frequency. And you can hear that that click sound has kind of turned into like more of a popping sound. And by moving this center frequency around, you can kind of change the tonal center of that pop. And by increasing this parameter, you're actually starting to make it ring. And if you look here at these coefficients, these are the feedback coefficients. You can see those floating point numbers getting higher, and that's what creates that ringing effect. In fact, you know, if we wanted to, we could turn this into an instrument. If we just like made a keyboard and converted the note numbers into a frequency to set the center frequency of this filter. You can now play this filter on a keyboard using an impulse signal. We could make a high pass filter with a lot of feedback. And you can really hear that cutoff frequency ringing. And because this is a high pass filter, you can hear the snappiness of the click still there, but the low frequency components of that sound are gone. Finally, let's take a look at a ready-made low-pass filter for a video signal. So in a video signal, the high-frequency components of the signal are the parts of it where the color values are changing rapidly. So when you see a lot of motion in a video, that means the color values in the pixels are like changing a lot, because the motion is the impression of motion is created by those pixels rapidly fluctuating. So Jit.slide does the same thing as the slide object we looked at earlier, but it does it pixel by pixel by pixel on color values in a matrix. And just like slide, it has these two parameters, which is an up and down parameter. So if we set them both to a low value, our output is very similar to the input. But if we increase them, we are starting to smooth out this video so that the parts of it that are rapidly changing are starting to go away. So if we made these like really high, our video is starting to like almost look like a still image. It's, you know, subtly moving, but really all of the rapidly changing parts of it are starting to disappear. And we could also, let's try a different video, this one. We could make like a low up value and a high down value. So this allows the colors to change up quickly, but they are slow to disappear, or vice versa. So that's sort of what a low pass filter on a video signal might look like. And here is the equation that Jit.slide is using. So y of n is equal to y of n minus 1 plus this, where it's the input signal minus y of n minus 1 divided by this slide factor. Okay, that's what we've got for you. Thank you for joining us. We will see you next time. Peace.